Municipal water accounts for up to 40% of a small farm's total operating costs. On a one-acre market garden, that translates to anywhere from $1,800 to $4,500 a year, depending on the region and the season. Year over year, that number only moves in one direction. Yet there is a specific agricultural infrastructure that eliminates this utility bill. It requires no booster pumps, it uses zero electricity, bypasses the pressurized municipal grid completely. The initial hardware to build the system costs less than $200. Once the components are connected and installed, the system operates indefinitely with almost no maintenance, driven by a physical force that never degrades. This is gravity-fed drip irrigation. It is nearly free, highly effective, and on most modern small farms and homesteads, it is entirely absent. The question is, why modern agriculture abandoned a mechanism that works so well? The mechanics of gravity-fed irrigation are deeply established in global agricultural history. Farmers in sub-Saharan Africa, the Middle East, and South Asia were directing water downhill through engineered channels long before the first motorized pump was manufactured. The Qanat systems of Iran offer some of the clearest proof of this principle. Some of these structures remain fully operational today after more than 2,500 years, moving groundwater across tens of kilometers using nothing but a carefully calculated grade and the relentless pull of gravity. The modern application for smallholder farms gained its clearest practical documentation in India during the late 1990s. Anand Rajwanshi, working through the National Institute for Rural Development in Maharashtra, published field trials demonstrating that a single elevated 1,000-liter tank could successfully drive subsurface drip tape. The results were remarkable. Yields for tomatoes, chili peppers, and leafy greens matched conventionally pressurized systems, while agricultural water use was 44% lower than traditional flood or furrow irrigation. Unfortunately, the study appeared in an agricultural engineering journal with extremely limited circulation. The findings never reached the marketing departments of commercial irrigation suppliers. A technology that is inexpensive to build and essentially self-operating is inherently difficult to commercialize. As a result, the system remained obscure because it generated no recurring revenue for equipment suppliers. The operating logic is straightforward. Water flows downhill. The engineering challenge lies in making that flow consistent and controllable throughout an entire crop cycle. A gravity-fed drip system requires 4 physical components: a storage tank to hold the water supply, an elevation structure to create pressure, a primary distribution header, and emitter lines placed directly in the crop root zone. Elevation is what converts stored water volume into usable pressure at ground level. A tank sitting at ground level provides almost no pressure at the emitter. Raising that tank by 1 meter generates approximately 0.1 bar of pressure. Raise the platform to 2.5 meters and you generate roughly 0.25 bar, placing the system within the operating range of many low-pressure drip irrigation products. Increase the elevation to 5 meters and the pressure reaches approximately 0.5 bar. That is enough pressure to drive standard commercial drip tape across roughly a quarter acre of active planting from a single reservoir. In 2014, the Indian Agricultural Research Institute evaluated these precise mechanics across multiple growing seasons. Their trials documented a 52% reduction in water use compared to conventional furrow irrigation. The improved water productivity allowed the entire system to recover its installation costs in just 14 months. The data confirmed the physics. When properly calibrated, an elevated tank can regulate water flow just as effectively as a mechanized pump. To understand why this proven system remains relatively unknown, it is necessary to examine the massive restructuring of rural infrastructure during the 20th century. In the 1930s and 40s, widespread electrification fundamentally changed agricultural production. Electric pumps solved the immediate challenge of lifting groundwater and pressurizing irrigation systems. They aligned perfectly with an industry rapidly reorganizing around mechanized, energy-intensive tools. This phenomenon is often referred to as infrastructure capture. Electric pumps require motors to service, electricity to purchase, and components to replace. A gravity-fed system generates none of those recurring expenses. The normal logic of markets dictates that long-lasting, self-operating tools are rarely promoted. That said, gravity-fed irrigation does have limitations that must be carefully considered. The primary constraint is topography. If the water source and the field are located on flat terrain, artificial elevation must be created. Constructing a reinforced timber or steel platform for the tank typically adds between $150 and $400 to the installation cost. The second limitation is maintenance. Because emitters operate at lower pressures, they lack the strong self-flushing capacity of motorized systems. Preventing sediment blockages requires proper filtration at the tank outlet and periodic manual flushing of line ends. These constraints are real. However, for many smallholders, the additional upfront effort represents a direct trade-off for long-term independence from utility costs. Independent farms operating today are already taking advantage of that trade-off. Consider a half-acre market garden in eastern Oregon producing salad greens and root vegetables for local distribution. In 2018, the owners removed their overhead sprinkler system and installed a 5,000-liter rainwater catchment tank mounted on a custom 4.5-meter timber frame. By relying entirely on rainfall collection and gravity-fed irrigation, they eliminated approximately $2,200 per year in pumping, electricity, and municipal water expenses. A similar transition occurred on a 1.2-hectare organic vegetable farm in southern Spain. The farm abandoned an aging and unreliable electric pumping system and instead utilized a natural spring located 6 meters above its production fields. The economics were compelling. The farm invested approximately €480 in piping, low-pressure drip tape, filters, and valves. In return, it reduced annual operating expenses by approximately €2,100. These farms are not exceptional cases. They represent the predictable outcome of evaluating a landscape, understanding its physical characteristics, and designing a system that works with the existing topography rather than against it. Transitioning to a gravity-fed model requires a methodical evaluation of the property. The first step is measuring available head pressure. Identify a location capable of supporting a water tank either on a natural slope or on a constructed platform positioned at least 2 meters above the highest crop row. The second step is calculating storage requirements. Vegetable crops typically consume between 3 and 6 liters of water per square meter during peak summer conditions. Multiply the cultivated area by that daily demand and size the tank to provide at least 3 to 5 days of reserve capacity. Once the tank and main header pipe are installed, the emitter lines can be laid. In hot climates, burying drip tape 5 to 10 centimeters below the surface significantly reduces evaporation losses and delivers moisture directly to the root zone where plants can use it most efficiently. The economics strongly favor the farmer. For a half-acre starter installation, including a 1,000-liter tank, structural lumber, a Y-strainer filter, polyethylene header pipe, valves, and low-flow drip tape, the initial hardware costs generally range from $218 to $342. The initial site assessment and construction require planning and labor, but once the water begins flowing, the recurring financial burden largely disappears. There's no electrical connection to maintain. There's no meter running in the background. If you have water and the ability to elevate it, the laws of physics do the rest. Calculate the elevation potential on your property before paying another utility bill. And if building agricultural independence through practical engineering interests you, continue exploring and sharing this research so it reaches the farmers who need it most.